Somewhere in the depths of space, a cloud of hydrogen gas spanning 100,000 light-years is beginning to collapse under its own gravity. This seemingly empty region, containing nothing but the simplest atoms in the universe, is about to become something extraordinary, a galaxy containing hundreds of billions of stars, countless planets, and possibly countless civilizations. What you're witnessing is the most fundamental act of cosmic creation, the transformation of primordial simplicity into breathtaking complexity. For over 13 billion years, this process has been occurring throughout the universe, turning the smooth, nearly featureless cosmos that emerged from the Big Bang into the rich tapestry of galactic structure rays we observe today. But here's what should keep you awake at night. We still don't fully understand how it happens. The transformation of gas clouds into galaxies involves physics so complex and scales so vast that even our most powerful supercomputers struggle to simulate the complete process. The numbers are staggering. A typical galaxy formation event involves the gravitational collapse of gas clouds containing the mass of a trillion suns. These clouds must cool from temperatures exceeding 10,000 degrees to just a few degrees above absolute zero while maintaining perfect balance between gravitational collapse and pressure support. The process requires dark matter scaffolding, magnetic field organization, stellar feedback regulation, and quantum mechanical cooling processes that operate across 20 orders of magnitude and scale. Yet, somehow, the universe makes it look effortless. Every major galaxy we observe, from massive ellipticals containing trillions of stars to delicate spirals like our own Milky Way, began as nothing more than slightly overdense regions in the primordial hydrogen and helium that filled the early cosmos. The fact that you exist to contemplate this process represents the successful outcome of billions of these cosmic construction projects operating over cosmic time. The European Space Agency's Planck mission has mapped the cosmic microwave background radiation with extraordinary precision, revealing the tiny temperature fluctuations that seeded galaxy formation. These fluctuations, just 0.001 degrees above absolute zero, represent quantum mechanical uncertainty amplified to cosmic proportions during cosmic inflation. From these infinitesimal beginnings, gravity has constructed every galaxy, star, planet, and living creature in the observable universe. Dr. Volker Sprengel's Millennium Simulation, the largest computer model of cosmic structure formation ever created, tracked the evolution of 10 billion dark matter particles over 13.6 billion years of cosmic history. The simulation reveals galaxy formation as an intricate dance between gravity, gas dynamics, and stellar feedback that creates fractal-like patterns of cosmic web filaments, galaxy clusters, and cosmic voids. Yet even this computational tour de force can only approximate the full complexity of how gas clouds become galaxies. The James Webb Space Telescope is now observing the earliest galaxies in the universe, formed just 400 million years after the Big Bang, when the cosmos was still young and wild. These primordial galaxies appear fundamentally different from modern ones, more chaotic, more actively star-forming, and more heavily influenced by the exotic conditions of the early universe. They provide direct evidence for how galaxy formation has evolved over cosmic time as the universe cooled and dark matter structures matured. But the mystery deepens when you consider the precision required for successful galaxy formation. The gas cooling rate must be perfectly balanced to fast and the gas collapses into black holes before stars can form, to slow and the gas disperses before gravitational collapse can occur. The dark matter halo must be massive enough to bind the gas gravitationally, but not so massive that it prevents cooling. The cosmic environment must be dense enough to provide gas inflow, but not so dense that galactic mergers disrupt the formation process. Recent observations have revealed that galaxy formation is far from a smooth, gradual process. The Atacama Large Millimeter Array ALMA has detected massive gas flows feeding early galaxies at rates exceeding 1,000 solar masses per year, enough to build an entire solar system every single day. These cosmic feeding systems operate through streams of cold gas that thread through the hot medium surrounding galaxies, creating supply lines that can sustain galaxy formation for billions of years. 3 major revelations await you in this cosmic journey. First, We'll discover how dark matter creates invisible scaffolding that guides gas flows across cosmic distances, forming the architectural framework upon which all cosmic structure builds. Second, we'll explore how quantum mechanical processes operating on atomic scales can determine the fate of gas clouds spanning hundreds of thousands of light years. And third, we'll reveal how stellar formation and galactic evolution create feedback loops so complex that galaxies essentially regulate their own growth through mechanisms we're only beginning to understand. If you're fascinated by the cosmic processes that created our galactic home and want to understand how the universe transforms simplicity into complexity, subscribe and hit the thumbs up button. And here is a question that will haunt you. If galaxy formation is so complex and requires such precise conditions, how did the universe manage to create billions of successful galaxies? Comment below with your thoughts. I'll pin the most insightful answer. This isn't just about ancient cosmic history. Understanding galaxy formation reveals fundamental principles about how complexity emerges from simplicity, how gravity shapes structure on the largest scales, and how the cosmic environment determines what kinds of galaxies can form in different epochs. The processes that created our Milky Way continue operating today, forming new galaxies in distant regions of space and reshaping existing ones through mergers and gas accretion. As we explore this cosmic construction process, we'll discover that galaxy formation represents one of the most remarkable examples of self-organization in nature. Without blueprints, central control, or external guidance, gravity somehow orchestrates the transformation of nearly uniform gas distributions into spectacular spiral arms, elliptical symmetries, and irregular structures that contain the building blocks of complexity throughout the universe. The story of how galaxies form from clouds of gas is ultimately the story of how the universe creates homes for stars, planets, and life itself. Every atom in your body was forged in stellar cores within galaxies that formed through the processes we'll explore. Understanding galaxy formation isn't just about cosmic evolution, it's about understanding the cosmic conditions that made your existence possible. The clouds of gas that will become tomorrow's galaxies are collapsing right now in distant regions of space, following the same physical laws that created our cosmic neighborhood billions of years ago. As we embark on this journey from primordial simplicity to galactic complexity, we'll discover that the universe's greatest magic lies not in exotic phenomena but in gravity's patient ability to transform the simplest ingredients into the most spectacular structures in existence. Now let's begin our exploration of cosmic construction on the grandest scale. Chapter 1: Primordial Seeds. In the beginning, there was almost nothing. The universe at 380,000 years after the Big Bang consisted of a nearly uniform sea of hydrogen and helium atoms floating in space at a temperature of about 3000 Kelvin, hot enough to melt copper, but cool enough for the first atoms to form from the plasma that had filled the cosmos since its birth. This primordial simplicity contained within it the seeds of every galaxy, star, and planet that would ever exist, hidden in temperature fluctuations so tiny they represented just 1 part in 100,000 variations from perfect uniformity. These cosmic seeds weren't randomly distributed. They emerged from quantum mechanical uncertainty during cosmic inflation, when the entire observable universe was smaller than a proton and quantum fluctuations were stretched to macroscopic scales by the exponential expansion of space itself. Dr. Alan Guthrie's inflationary theory explains how these microscopic quantum jitters became the cosmic scaffolding upon which all future structure would build. Without inflation to amplify quantum uncertainty, the universe would have remained perfectly smooth and featureless forever. The European Space Agency's Planck mission has mapped these primordial seeds with extraordinary precision, revealing patterns that encode the cosmic conditions when the universe was less than a billionth of a billionth of a billionth of a second old. The cosmic microwave background radiation preserves a snapshot of these fluctuations like a cosmic fossil, showing us the exact distribution of matter and energy that would eventually become galaxy clusters, cosmic web filaments, and the cosmic voids between them. But these seeds represented more than just density variations. They encoded information about the fundamental nature of space, time, matter, and energy in the early universe. The size, amplitude, and distribution of primordial fluctuations reveal that the universe contains approximately 5 times more dark matter than normal matter. That space itself is geometrically flat to extraordinary precision, and that cosmic inflation occurred with parameters fine-tuned to produce the complex structures we observe today. Dr. Joseph Silk's calculations show that if the primordial fluctuations had been just slightly smaller, gravity would never have overcome the expansion of space and no galaxies would have formed. If they had been slightly larger, the universe would have collapsed into black holes before stars could ignite. The observed amplitude of cosmic seeds falls within the narrow range that permits both gravitational collapse and long-term stability, a cosmic Goldilocks condition that appears to be exactly right for creating a universe rich in structure and complexity. The seeds weren't uniformly distributed but showed subtle patterns that would determine the large-scale structure of the universe billions of years later. Regions destined to become massive galaxy clusters already showed enhanced density in the primordial fluctuations, while areas that would become cosmic voids contained less matter than average. These patterns followed statistical distributions predicted by inflation theory with remarkable precision, providing our strongest evidence that cosmic inflation actually occurred. Recent analysis of cosmic microwave background polarization has revealed additional information encoded in the primordial seeds. The polarization patterns show how photons were scattered by electrons in the early universe, preserving information about the velocity patterns of matter at the time of recombination. These velocity seeds complemented the density seeds, creating the initial conditions for both gravitational collapse and the rotational motions that would eventually create spiral galaxy structure. The transformation of these seeds into actual cosmic structures required dark matter to serve as gravitational scaffolding, while normal matter remained tightly coupled to photons through electromagnetic interactions and couldn't collapse under gravity until after recombination. Dark matter felt only gravitational forces and began clustering immediately after inflation. By the time normal matter could finally participate in gravitational collapse, dark matter had already created potential wells that determine where galaxies would form. Computer simulations of structure formation, such as the Millennium simulation, show how primordial seeds evolved into cosmic web structure through gravitational amplification. Small overdensities grew larger as they attracted surrounding matter through gravitational attraction. Meanwhile, underdense regions became more empty as matter flowed toward the growing concentrations. This gravitational instability operated like a cosmic feedback loop, systematically amplifying the tiny variations present in the primordial universe. The process wasn't smooth or gradual but proceeded through a complex hierarchy of structure formation. The smallest dark matter halos formed first, followed by progressively larger structures as gravity continued pulling matter together. This bottom-up structure formation created a fractal-like cosmic web where small structures merged to form larger ones in an ongoing process that continues today. Every galaxy we observe represents the descendant of countless smaller structures that merged over billions of years. But the seeds contained information beyond just matter density. Magnetic field fluctuations in the primordial plasma created seed magnetic fields that would eventually be amplified into the galactic magnetic fields we observe today. Acoustic oscillations in the photon boron fluid created pressure waves that influenced where normal matter would accumulate relative to dark matter concentrations. Even the ratio of matter to antimatter was determined by particle physics processes during the first microseconds after the Big Bang. The Cosmic Assembly Near-Infrared Deep Extragalactic Legacy Survey Candles has traced galaxy formation back to within 600 million years of the Big Bang, revealing how the first galaxies formed from primordial seeds. These early galaxies appear small, irregular, and actively star-forming compared to mature galaxies today. They represent the direct descendants of the first dark matter halos that became massive enough to trap and cool primordial gas. Dr. Michael Norman's simulations of primordial galaxy formation show how the first stars formed within dark matter mini-hollows containing just 1 million times the mass of the Sun. These population 3 stars were fundamentally different from modern stars composed of pure hydrogen and helium. They burned much hotter and died much faster than any stars forming today. Their explosive deaths created and dispersed the first heavy elements, seeding future star formation with the chemical complexity necessary for planet formation and life. The primordial seeds also encoded the cosmic web structure that guides galaxy formation today. Filaments of dark matter stretch between galaxy clusters like cosmic highways, channeling gas flows that feed galaxy formation over billions of years. The intersection points of these filaments became the preferred locations for massive galaxy formation, while galaxies forming along filament branches typically remain smaller and less massive. Recent observations from the Sloan Digital Sky Survey reveal that galaxy properties today still correlate with the primordial environment encoded in cosmic microwave background fluctuations. Galaxies that formed in regions with higher primordial density tend to be more massive, contain older stellar populations, and show less active star formation than galaxies that formed in average density regions. This cosmic memory effect demonstrates how conditions in the primordial universe continue influencing galaxy evolution billions of years later. The study of primordial seeds has also revealed deep connections between cosmic structure formation and fundamental physics. The statistical properties of cosmic microwave background fluctuations provide constraints on inflation physics, dark matter properties, and the nature of dark energy. These observations have ruled out many theoretical models of the early universe while pointing toward new physics that operates at energy scales far beyond anything achievable in terrestrial laboratories. Looking forward, next-generation cosmic microwave background experiments like the Simons Observatory will measure primordial seed properties with even greater precision, potentially detecting signatures of primordial gravitational waves, exotic dark matter interactions, or new particles that influence cosmic inflation. These observations may reveal whether our universe is unique or part of a vast multiverse containing regions with different physical laws and structure formation histories. The remarkable aspect of primordial seeds is their universality. The same quantum mechanical processes that created density fluctuations in our cosmic neighborhood also operated in the most distant regions of the observable universe. This cosmic democracy means that galaxy formation follows the same basic principles throughout space and time, creating a universe where complexity can emerge anywhere the conditions are right. Understanding primordial seeds reveals how the universe creates complexity from simplicity through gravitational amplification of quantum mechanical uncertainty. The tiny fluctuations that emerged from inflation contained within them the potential for every galaxy, star, and planet that would ever exist. These cosmic seeds represent the universe's initial blueprint for structure formation, a blueprint written in the quantum mechanical language of uncertainty and amplified by cosmic inflation into the foundation for all cosmic architecture. The transformation of primordial seeds into actual galaxies required billions of years and involved physics spanning scales from quantum mechanics to cosmic expansion. But the essential information that determined which regions of space would become galaxies and which would remain empty was encoded in the universe when it was less than a second old, demonstrating how quantum mechanical events in the earliest moments of cosmic history continue shaping structure formation today. Chapter 2. Dark Scaffolding. Invisible architecture governs cosmic construction. While primordial seeds provided the blueprint for structure formation, dark matter created the scaffolding that actually built galaxies from clouds of gas. This mysterious substance, comprising 85% of all matter in the universe, doesn't emit or absorb electromagnetic radiation, making it effectively invisible to every telescope ever constructed. Yet without dark matter's gravitational scaffolding, no galaxy would ever have formed, and the universe would have remained a cold, empty expanse of primordial gas forever. The existence of dark matter scaffolding was first inferred from observations that defied conventional physics. Dr. Fritz Zwickie's 1933 study of the Coma cluster revealed that galaxies were moving too fast to be gravitationally bound by the visible matter alone. The cluster should have dispersed long ago unless some invisible substance provided additional gravitational binding. Zwickie's missing mass represented the first evidence that cosmic structure formation required more than the familiar matter composed of protons, neutrons, and electrons. But dark matter's role extends far beyond simply providing additional gravity. Computer simulations of structure formation reveal that dark matter creates the cosmic web, a vast network of filaments and halos that guides matter flows across billions of light years. This invisible architecture determines not just where galaxies form, but what kinds of galaxies can form in different cosmic environments. The cosmic web represents the universe's hidden skeleton, supporting all visible structure through purely gravitational interactions. Dr. Volker Sprengel's Millennium simulation tracked the evolution of 10 billion dark matter particles from shortly after the Big Bang to the present day, revealing how dark matter scaffolding develops over cosmic time. Small-scale structure forms first as tiny fluctuations in dark matter density grow through gravitational attraction. These early dark matter mini-hollows merge hierarchically to create progressively larger structures, eventually forming the massive dark matter halos that host individual galaxies and galaxy clusters. The scaffolding process operates through gravitational collapse that begins long before normal matter can participate in structure formation. While primordial hydrogen and helium remain coupled to photons and could collapse gravitationally until 380,000 years after the Big Bang, dark matter felt only gravitational forces and began clustering immediately. By the time normal matter finally decoupled from photons during recombination, dark matter had already created deep gravitational potential wells that determine where gas could accumulate and cool. Recent observations from gravitational lensing surveys reveal the detailed architecture of dark matter scaffolding with unprecedented precision. When light from distant galaxies passes through massive dark matter structures, it bends according to Einstein's general relativity, creating distorted images that map the invisible matter distribution. The Dark Energy Survey has used this gravitational lensing technique to map dark matter structure across billions of light years, revealing a cosmic web of extraordinary complexity. The scaffolding exhibits fractal-like properties that operate across all scales from individual galaxy halos to massive superclusters. Dark matter halos contain subhalos, which contain sub-subhalos, and a hierarchical structure that reflects the gravitational merging history of cosmic structure formation. This self-similar architecture means that the same physical processes that created galaxy-scale dark matter halos also operated on smaller scales to create the substructure that influences star formation within individual galaxies. The Aquarius project simulations have revealed the internal structure of dark matter halos in extraordinary detail, showing how merging events create streams, shells, and other substructures that persist for billions of years. When smaller dark matter halos merge with larger ones, they don't simply disappear but remain detectable as gravitational substructure within the larger halo. This fossil record of past mergers determines how gas flows within galaxies and influences ongoing star formation patterns. Dark matter scaffolding also exhibits dynamic properties that actively influence galaxy formation rather than providing passive gravitational support. As dark matter halos grow through mergers and accretion, they heat the surrounding gas through gravitational compression and shock waves. This halo heating can shut off galaxy formation by preventing gas cooling, explaining why the most massive dark matter halos often contain surprisingly small galaxies relative to their total mass. The Via Lactea simulations of Milky Way-sized dark matter halos reveal scaffolding structure that extends far beyond the visible galaxy. Our Milky Way sits at the center of a dark matter halo that contains hundreds of smaller subhalos, many of which likely hosted dwarf galaxies that were subsequently disrupted by tidal forces. The gravitational influence of this invisible scaffolding determines the orbits of satellite galaxies, stellar streams, and even influences the solar system's motion through the galaxy. Recent observations have detected the gravitational effects of dark matter scaffolding on scales ranging from individual galaxies to cosmic superclusters. The bullet cluster observation shows dark matter separating from normal matter during a cluster collision, proving that dark matter interacts primarily through gravity rather than electromagnetic forces. This gravitational-only interaction allows dark matter to create scaffolding that normal matter follows but cannot significantly influence in return. The cosmic web architecture created by dark matter scaffolding shows remarkable correlation with the distribution of galaxies across cosmic space. Galaxy surveys reveal that visible matter traces dark matter filaments like Christmas lights strung along invisible wires. The cosmic web's largest structures, galaxy walls spanning hundreds of millions of light-years, mark regions where dark matter filaments intersect and create enhanced gravitational attraction that draws gas and galaxies into sheet-like configurations. Dr. Reza Wexler's analysis of galaxy formation within dark matter scaffolding reveals how halo properties determine galaxy characteristics. Galaxies forming within more massive dark matter halos tend to be larger, more massive, and contain older stellar populations than galaxies in smaller halos. The relationship between halo mass and galaxy mass follows tight correlations that suggest galaxy formation efficiency depends critically on the gravitational environment provided by dark matter scaffolding. The scaffolding also creates preferred directions for galaxy formation through cosmic web filaments that channel gas flows across vast distances. The Cosmic Web Reconstruction Survey has mapped these invisible highways, revealing how dark matter filaments connect galaxy clusters and guide the formation of galaxy groups along cosmic superhighways. Gas flowing along these filaments can travel thousands of times farther than it could move under its own thermal pressure, enabling galaxy formation in regions that would otherwise remain empty. Future observations will probe dark matter scaffolding with unprecedented detail through next-generation gravitational lensing surveys and direct detection experiments. The Large Synoptic Survey Telescope will map weak gravitational lensing across the entire southern sky, revealing dark matter substructure down to galaxy-scale masses. Meanwhile, underground dark matter detection experiments continue searching for direct evidence of dark matter particle interactions that could reveal the fundamental nature of this cosmic scaffolding. Material. The most profound aspect of dark matter scaffolding is its role as cosmic architecture that operates entirely through gravitational forces. Unlike electromagnetic forces that create structure through complex interactions between charged particles, dark matter builds cosmic scaffolding through pure gravitational attraction, the weakest fundamenta. A force operating over the largest distances to create the universe's most massive structures. Laboratory experiments with ultra-cold atomic gases are beginning to simulate dark matter-like behavior, revealing how gravitational interactions alone can create complex structural patterns. These experiments show that purely gravitational systems naturally develop hierarchical clustering, filamentary structure, and other properties observed in cosmic dark matter distributions. The universality of gravitational clustering suggests that dark matter scaffolding represents an inevitable consequence of any gravitationally interacting substance in an expanding universe. The study of dark matter scaffolding has revealed deep connections between cosmic structure formation and fundamental physics. The properties of dark matter particles, their mass, interaction strength, and thermal velocity determine the smallest scales on which structure can form and the efficiency with which dark matter can capture and retain normal matter. These connections mean that observations of cosmic structure formation provide constraints on particle physics models that complement terrestrial accelerator experiments. Understanding dark matter scaffolding is crucial for predicting the future evolution of cosmic structure. As dark energy accelerates cosmic expansion, dark matter halos will become increasingly isolated, and galaxy formation will eventually cease as the universe expands beyond the point where new structure can form. The scaffolding that enabled galaxy formation throughout cosmic history will eventually be torn apart by the accelerating expansion of space itself. The invisible architecture of dark matter scaffolding represents one of the universe's most remarkable engineering projects, a cosmic construction system that builds galactic structure through gravitational forces alone operating over billions of years to create the framework that supports all visible matter. Without this dark scaffolding, the universe would contain no galaxies, no stars, no planets, and no observers to contemplate the cosmic construction process that made their existence possible. Chapter 3: Gravitational Collapse. Gravity transforms gentle suggestion into cosmic compulsion. Within the protective embrace of dark matter halos, primordial gas clouds begin the slow but inexorable journey toward galactic birth through gravitational collapse, a process so fundamental yet so complex that it determines not just whether galaxies form but what kinds of galaxies emerge from the cosmic construction process. This cosmic compression operates through physics that spans 20 orders of magnitude in scale. From quantum mechanical cooling processes within individual atoms to the grand choreography of matter flows across hundreds of thousands of light years. The collapse begins subtly, almost imperceptibly. Gas flowing along dark matter filaments encounters the gravitational potential wells created by massive dark matter halos. Initially, this gas moves at speeds exceeding 200 kilometers per second, fast enough to escape most planetary gravitational fields. But the dark matter halo's gravity gradually decelerates these cosmic winds, allowing gas to accumulate within the halo's gravitational embrace. This process of gas accretion can continue for billions of years, slowly building the material reservoir from which galaxies form. Dr. Frank van den Bosch's analytical models of halo gas accretion reveal the delicate balance required for successful gravitational collapse. The gas must cool efficiently to reduce thermal pressure that opposes gravitational contraction, but cooling too rapidly creates problems of its own. If gas loses thermal energy faster than gravity can organize its collapse, it falls directly toward the halo's center and potentially forms a supermassive black hole rather than a galaxy. Successful galaxy formation requires a cooling rate that perfectly matches the gravitational free-fall timescale. The European Space Agency's XMM Newton X-ray telescope has observed this cosmic balancing act in nearby galaxy clusters, where hot gas with temperatures exceeding 10 million degrees slowly cools and flows toward cluster centers. These cooling flows can transport hundreds of solar masses per year towards central galaxies, providing the raw material for continued star formation. But the process is self-regulating. As gas accumulates and forms stars, the energy released by stellar processes can reheat the surrounding medium and temporarily halt further collapse. Gravitational collapse operates differently at different cosmic epochs due to the evolving properties of the cosmic environment. In the early universe, when cosmic expansion was decelerating due to matter domination, gravitational collapse could proceed more efficiently than today. Gas clouds could grow larger and denser before cosmic expansion pulled them apart. This explains why early galaxies often appear more actively star-forming and chaotic than modern galaxies formed in today's dark energy-dominated cosmos. The collapse process creates complex hydrodynamic phenomena as gas flows converge from multiple directions within dark matter halos. Computer simulations by Dr. Lucio Mayer's group show how gas streams threading through dark matter scaffolding can maintain surprisingly low temperatures even as they fall into deep gravitational potential wells. These cold streams avoid heating through shock waves by following the paths of least resistance through the dark matter distribution, creating laminar flows that can deliver pristine gas directly to forming galactic disks. Recent observations from the Atacama Large Millimeter Array ALMA have detected these cold gas streams directly, revealing massive flows of molecular hydrogen falling into distant galaxies at rates exceeding the mass of our Sun every few hours. These observations confirm theoretical predictions that galaxy formation requires sustained gas accretion over cosmic time rather than single catastrophic collapse events. Galaxies grow through cosmic dining, continuously consuming gas from their surroundings rather than forming from isolated, self-contained gas clouds. The direction and angular momentum of gravitational collapse determine whether forming galaxies become spiral disks, elliptical spheroids, or irregular structures. Gas flowing along cosmic web filaments naturally possesses angular momentum from large-scale tidal torques generated by surrounding matter distributions. As this gas collapses gravitationally, conservation of angular momentum spins it faster, potentially creating centrifugally supported disks that resist further collapse in directions perpendicular to T rotation axis. Dr. Avishai Dekol's models of galaxy formation reveal how the cosmic web's geometry influences galaxy morphology through the angular momentum of accreting gas. Gas flowing along single filaments into dark matter halos tends to create disk galaxies with well-defined rotation patterns. But gas accreting from multiple directions or through major merger events creates more spherical distributions that become elliptical galaxies. The cosmic web's local architecture essentially predetermines what kinds of galaxies can form in different environments. Gravitational collapse also amplifies magnetic fields that were present as tiny seeds in the primordial universe. As gas clouds contract under gravity, frozen and magnetic fields become compressed and twisted, potentially reaching strengths millions of times greater than the original cosmic magnetic field. These amplified magnetic fields can influence gas dynamics, provide pressure support against continued collapse, and create the galactic magnetic field structures observed in modern galaxies. The collapse process involves complex feedback loops between gravity, gas dynamics, magnetic fields, and turbulence that make galaxy formation predictions extremely challenging. Turbulent motions within collapsing gas clouds can either enhance or suppress gravitational collapse depending on the scale and energy of the turbulence. Understanding these multi-physics interactions requires computational simulations that push the limits of the world's most powerful supercomputers. Recent simulations by the FIRE collaboration have achieved unprecedented realism in modeling gravitational collapse and galaxy formation by including detailed treatments of stellar feedback, magnetic fields, and turbulent gas dynamics. These simulations show that successful galaxy formation requires precise balance between gravitational collapse, gas cooling, star formation, and stellar feedback processes. Small changes in any of these processes can dramatically alter the final galaxy properties or even prevent galaxy formation entirely. The efficiency of gravitational collapse varies dramatically with dark matter halo mass, creating distinct populations of galaxies with different formation histories. Low-mass halos can retain gas efficiently and form galaxies with high gas fractions and active star formation. Intermediate mass halos like those hosting the Milky Way achieve optimal collapse efficiency and form massive disk galaxies. Very massive halos heat accreting gas so strongly that cooling becomes inefficient, resulting in gas-poor elliptical galaxies dominated by old stellar populations. Observations from the Hubble Space Telescope's Candles survey reveal how gravitational collapse efficiency has evolved over cosmic time. Early galaxies appear more compact and densely packed than modern galaxies, suggesting that collapse proceeded more efficiently in the higher density environment of the young universe. As cosmic expansion accelerated due to dark energy dominance, gravitational collapse became less efficient, leading to the larger, more diffuse galaxy structures observed today. The cosmic microwave background observations provide constraints on gravitational collapse through measurements of secondary temperature fluctuations caused by hot gas in galaxy clusters. The thermal Sunyov-Zeldovich effect reveals where gravitational collapse has heated gas to X-ray temperatures, mapping the locations and masses of collapsed structures across cosmic space. These observations complement galaxy surveys by detecting collapsed structures regardless of whether they contain luminous galaxies. Future observations will probe gravitational collapse during galaxy formation through next-generation telescopes capable of observing the earliest epochs of cosmic history. The James Webb Space Telescope is already detecting galaxies forming just 400 million years after the Big Bang, revealing how gravitational collapse operated in cosmic environments very different from today. These observations may reveal whether early galaxy formation followed the same physical principles operating today or required different physics in the exotic conditions of the early universe. Understanding gravitational collapse has profound implications for predicting the future evolution of cosmic structure. As dark energy accelerates cosmic expansion, new gravitational collapse will become increasingly difficult as gas clouds are stretched beyond the point where gravity can overcome cosmic expansion. Eventually, all galaxy formation will cease as the universe expands beyond the critical density required for continued gravitational collapse. The study of gravitational collapse is also revealing deep connections between cosmic structure formation and fundamental physics. The efficiency of gas cooling during collapse depends on atomic and molecular physics processes that operate on quantum mechanical scales. The balance between collapse and stellar feedback involves nuclear physics that governs stellar evolution and supernova explosions. These connections mean that galaxy formation provides tests of fundamental physics under conditions impossible to reproduce in terrestrial laboratories. Gravitational collapse represents the universe's primary mechanism for creating complexity from simplicity, transforming smooth distributions of primordial gas into the intricate structures that populate galactic ecosystems. This cosmic compression operates through gravitational forces. that amplify tiny density fluctuations into massive concentrated structures while preserving the angular momentum and magnetic field configurations that determine final galaxy properties. The delicate balance required for successful gravitational collapse reveals why galaxy formation is simultaneously ubiquitous throughout cosmic space and precisely calibrated to create the diverse galaxy population we observe today. Chapter 4: Cosmic Chemistry. The universe had to learn chemistry from scratch. In the beginning, cosmic gas contained only the simplest elements, hydrogen and helium, forged during the first few minutes after the Big Bang. But galaxy formation required far more complex chemistry, involving molecules that could cool hot gas through radiative processes, dust grains that could catalyze chemical reactions, and heavy elements that would eventually enable planet formation and life. The cosmic chemistry that transforms primordial gas into galaxies represents one of the universe's most remarkable educational achievements. The first lesson in cosmic chemistry began with the formation of molecular hydrogen, H, to the simplest molecule in the universe, but also the most important for early galaxy formation. Dr. Abraham Loeb's calculations show that molecular hydrogen formation proceeds through surprisingly complex pathways involving negative hydrogen ions H and free electrons. In the primordial universe, this process occurred with glacial slowness, taking millions of years to convert even a tiny fraction of atomic hydrogen into molecular form. But molecular hydrogen was crucial because it provided the first efficient cooling mechanism for primordial gas clouds. While atomic hydrogen can cool only through highly inefficient collisional processes, molecular hydrogen possesses vibrational and rotational energy states that enable rapid cooling through infrared radiation emission. This cooling allows gravitational collapse to proceed by reducing the thermal pressure that opposes compression under gravity. The formation of the first stars represented a dramatic acceleration in cosmic chemical education. These population 3 stars, composed entirely of hydrogen and helium, burned much hotter and died much more explosively than any stars forming today. Dr. Volcker-Brahms simulations show that these primordial stars could reach masses exceeding 200 times our Sun, creating nuclear furnaces so intense they forged elements far up the periodic table before exploding as hypernovae that enriched surrounding gas with the first heavy elements. These stellar explosions created cosmic chemistry lessons that propagated across vast distances. When population 3 stars died, they dispersed newly forged carbon, oxygen, silicon, and iron into the surrounding gas clouds through supernova shock waves that could travel thousands of light-years far. On the explosion sites, this chemical enrichment fundamentally changed the physics of subsequent gas cooling and star formation by providing new pathways for energy dissipation. The Atacama Large Millimeter Array ALMA has detected carbon monoxide and other molecules in galaxies observed when the universe was less than 1 billion years old, revealing that cosmic chemistry evolved rapidly once the first stellar nucleosynthesis began. These early molecules enabled much more efficient cooling than pure hydrogen and helium, allowing gas clouds to reach the low temperatures necessary for forming the first disk galaxies with well-organized stellar populations. Dust grain formation represented another crucial advancement in cosmic chemistry education. When gas enriched with heavy elements cools sufficiently, atoms of carbon, oxygen, silicon, and iron can condense into solid particles just nanometers in size. These dust grains dramatically enhance gas cooling efficiency by providing surfaces for molecular formation and by absorbing ultraviolet radiation and re-emitting it as infrared energy that escapes easily from dense gas clouds. Recent observations from the Herschel Space Observatory reveal that dust formation occurs remarkably quickly after stellar nucleosynthesis begins. Galaxies observed just 700 million years after the Big Bang already contain substantial dust populations, suggesting that cosmic chemistry mastered dust grain physics within a few hundred million years of the first stellar explosions. This rapid dust enrichment enabled the formation of molecular clouds similar to those that create stars in modern galaxies. The cosmic chemistry curriculum expanded dramatically with the formation of complex molecules in the interstellar medium. Radio astronomy observations have identified over 200 different molecular species in galactic gas clouds. ranging from simple diatomic molecules like carbon monoxide to complex organic compounds containing dozens of atoms. This molecular complexity provides multiple pathways for gas cooling and creates the chemical foundation for eventual planet formation and abiogenesis. Dr. Yuan van Dishoek's laboratory studies of interstellar chemistry reveal how cosmic gas clouds function as vast chemical laboratories where molecules form through gas phase reactions, grain surface catalysis, and photochemical processes driven by stellar ultraviolet radiation. The chemistry operates under extreme conditions, temperatures near absolute zero, densities millions of times lower than Earth's atmosphere, and radiation fields that would sterilize any terrestrial environment. The chemical evolution of galaxies creates feedback loops that regulate star formation efficiency over cosmic time. As stellar nucleosynthesis produces heavy elements, the enhanced cooling they enable allows gas clouds to form stars more efficiently. But increased star formation also increases the rate of stellar explosions, which can heat and disperse gas clouds, temporarily suppressing further star formation. This chemical feedback creates the cyclical patterns of star formation observed in many galaxies. Observations from the Spitzer Space Telescope reveal how cosmic chemistry varies with galactic environment. Galaxies in dense cluster environments often show reduced molecular gas fractions compared to isolated galaxies, suggesting that environmental effects influence chemical evolution pathways. Galaxy interactions can trigger enhanced star formation that rapidly converts gas into stars, while tidal stripping can remove gas before chemical enrichment reaches equilibrium levels. The role of magnetic fields in cosmic chemistry represents an emerging frontier in galaxy formation studies. Magnetic fields can influence the formation and survival of molecules by affecting gas dynamics and shielding molecules from dissociating radiation. Recent simulations by Dr. Stelloffner's group show that magnetic fields create filamentary structures in molecular clouds that enhance star formation efficiency by concentrating gas into dense clumps, where gravitational collapse can proceed rapidly. Cosmic ray chemistry provides another layer of complexity to galactic chemical evolution. High-energy particles accelerated by supernova explosions and other violent galactic processes can ionize interstellar gas, break apart molecules, and drive chemical reactions that wouldn't occur under normal conditions. The cosmic ray ionization rate determines the balance between molecular formation and destruction, influencing gas cooling efficiency and star formation rates throughout galactic evolution. The European Space Agency's Gaia mission has revealed chemical gradients within our Milky Way that preserve fossil records of cosmic chemistry education over billions of years. Stars in the galactic center contain higher heavy element abundances than stars in the outer disk, reflecting the inside-out chemical enrichment pattern that occurred during our galaxy's formation. These chemical archaeology studies reveal how cosmic chemistry evolved spatially as well as temporally during galaxy assembly. Recent discoveries of extremely metal-poor stars in the galactic halo provide direct samples of cosmic chemistry from very early epochs. These fossil stars, containing less than 1/10,000th the heavy element abundance of the Sun, formed when cosmic chemistry was still in its infancy. Their chemical compositions preserve information about the first stellar explosions and reveal how cosmic nucleosynthesis proceeded, when the universe contained only the products of population 3 stellar nucleosynthesis. The study of cosmic chemistry in external galaxies reveals how chemical evolution depends on galactic mass, star formation history, and environmental conditions. Dwarf galaxies often show lower heavy element abundances than massive galaxies, reflecting their lower star formation efficiency and greater susceptibility to gas loss through stellar winds and supernova explosions. These observations constrain models of how cosmic chemistry education varies with galactic properties. Future observations will probe cosmic chemistry during the earliest epochs of galaxy formation through infrared and millimeter wave observations of molecular emission lines. The James Webb Space Telescope can detect carbon monoxide and other molecules in galaxies at redshifts exceeding 6, when the universe was less than 1 billion years old. These observations will reveal how quickly cosmic chemistry advanced from primordial simplicity to molecular complexity. Laboratory astrochemistry experiments are beginning to reproduce the extreme conditions of interstellar space, revealing how molecules form and survive in cosmic environments. These experiments show that grain surface chemistry can proceed efficiently even at temperatures just a few degrees above absolute zero, explaining how complex molecules can form in the coldest regions of galactic gas clouds where star formation eventually occurs. The implications of cosmic chemistry extend far beyond galaxy formation to questions about the chemical prerequisites for life throughout the universe. The heavy elements forged in stellar cores and dispersed by supernova explosions provide the raw materials for rocky planet formation, while the complex molecules formed in galactic gas clouds may seed the chemical pathways that lead to abiogenesis on suitable worlds. Understanding cosmic chemistry reveals how the universe creates complexity through nuclear physics operating in stellar cores and through molecular physics operating in galactic gas clouds. This chemical education program has operated continuously for over 13 billion years, gradually enriching galactic environments with the elements and molecules necessary for increasingly complex structure. Ray formation. The cosmic chemistry that enabled galaxy formation also created the chemical foundation for every technological civilization that might arise within those galaxies, demonstrating deep connections between stellar nucleosynthesis, galactic evolution, and the emergence of complexity throughout the cosmos. Chapter 5: Stellar Ignition. The universe learns to shine. After billions of years of cosmic chemistry lessons and gravitational architecture, galactic gas clouds finally achieve the conditions necessary for stellar ignition, the moment when nuclear fusion transforms ordinary matter into cosmic furnaces that illuminate the universe and fundamentally alter galaxy formation through the energy they release. This stellar awakening represents the universe's transition from dark, gas-dominated structures to the luminous galaxies we observe today, powered by nuclear reactions that convert mass directly into energy according to Einstein's most famous equation. The first stellar ignition events occurred within the smallest dark matter halos, capable of cooling primordial gas to temperatures low enough for gravitational collapse to overcome thermal pressure. Dr. Naoki Yoshida's simulations show that these first stellar nurseries contain just a few million times the mass of our Sun, tiny by galactic standards but sufficient to trigger the nuclear fusion reactions that would transform cosmic evolution forever. The collapse of gas within these mini hollows created temperatures and densities extreme enough to overcome the electromagnetic repulsion between protons and initiate hydrogen burning. But stellar ignition in the primordial universe differed dramatically from star formation today. Without heavy elements to provide efficient cooling, primordial gas clouds could not fragment into the small, low-mass stars that dominate modern stellar populations. Instead, the first stars were behemoths of massive, hot, and short-lived nuclear reactors that burned through their fuel in just a few million years before exploding as hypernovae that fundamentally altered the cosmic environment. The death of these population 3 stars represented the universe's first lesson in stellar feedback, the process by which stellar energy output regulates subsequent star formation. When the first massive stars exploded, they released energy equivalent to billions of hydrogen bombs detonating every second for months, creating shock waves that heated surrounding gas to millions of degrees and potentially disrupted star formation in neighboring gas clouds for hundreds of millions of years. Recent observations from the James Webb Space Telescope are beginning to detect the signatures of these first stellar ignition events in the most distant galaxies observable. These early galaxies appear surprisingly luminous and actively star-forming, suggesting that stellar ignition proceeded efficiently despite the challenging conditions of the primordial universe. The rapid pace of early star formation implies that stellar feedback mechanisms had not yet evolved the self-regulating properties observed in modern galaxies. The transition from population 3 to population to star formation marked a crucial phase change in cosmic evolution. Once the first stellar explosions enriched surrounding gas with heavy elements, stellar ignition could proceed through dramatically different pathways. Carbon and oxygen atoms enabled much more efficient gas cooling, allowing smaller gas clouds to collapse gravitationally and form lower-mass stars with longer lifetimes and gentler feedback effects. Dr. John Wise's simulations of early galaxy formation reveal how stellar feedback creates bubbles of hot, metal-enriched gas that can extend far beyond the star-forming regions where they originate. These feedback bubbles can trigger star formation in surrounding gas clouds through compression effects while simultaneously heating other regions enough to prevent star formation entirely. This creates complex patterns of triggered and suppressed star formation that determine where and when stellar ignition occurs within forming galaxies. The efficiency of stellar ignition depends critically on the balance between gas cooling and stellar heating within galactic environments. Computer models by the Fire Collaboration show that galaxies maintain roughly constant gas temperatures through self-regulation when star formation rates increase. The additional stellar feedback heats gas and reduces cooling efficiency, naturally limiting further star formation. This thermostat-like behavior prevents galaxies from converting all their gas into stars too rapidly. Stellar ignition also requires the formation of molecular hydrogen, which serves as the primary coolant for gas clouds in low metallicity environments. Recent observations from ALMA reveal vast reservoirs of molecular gas in high-redshift galaxies, confirming that stellar ignition can proceed efficiently even when heavy element abundances remain much lower than those observed in modern galaxies. This molecular gas provides the immediate fuel reservoir from which individual stars form through further gravitational collapse. The spatial patterns of stellar ignition within galaxies reflect the complex interplay between gas dynamics, magnetic fields, turbulence, and stellar feedback. High-resolution simulations show that star formation often proceeds in waves that propagate across galactic disks, triggered by spiral density waves, supernova explosions, or galaxy interactions that compress gas beyond the threshold density required for gravitational collapse. Recent studies of stellar populations in nearby galaxies reveal fossil evidence for how stellar ignition patterns evolve over cosmic time. The Hubble Space Telescope's observations of resolved stellar populations show that many galaxies experience periods of enhanced star formation followed by quiescent phases, with reduced stellar ignition rates. These star formation histories preserve information about how stellar feedback evolved as galaxies assembled through mergers and gas accretion. The role of supermassive black holes in regulating stellar ignition represents one of the most surprising discoveries in modern galaxy formation studies. As gas falls toward galactic centers, it can feed supermassive black holes that release enormous amounts of energy through accretion processes. This active galactic nucleus feedback can heat gas throughout the entire galaxy, effectively shutting off stellar ignition across the entire system. The correlation between supermassive black hole masses and galactic bulge masses suggests that this black hole feedback plays a crucial role in determining final galaxy properties. Magnetic fields add another layer of complexity to stellar ignition by influencing how gas flows and fragments within star-forming regions. Observations from radio telescopes reveal that galactic magnetic fields are often organized into large-scale patterns that can either enhance or suppress star formation, depending on the field geometry. Magnetic pressure can provide additional support against gravitational collapse, requiring higher gas densities for stellar ignition to occur. The initial mass function, the distribution of stellar masses that result from stellar ignition, appears to vary with cosmic environment and epoch. Early stellar populations often show top-heavy mass functions with more massive stars than observed in modern star-forming regions. This evolution in stellar ignition patterns has profound implications for galactic chemical evolution, stellar feedback efficiency, and the production of compact stellar remnants like neutron stars and black holes. Recent discoveries of extremely luminous galaxies in the early universe suggest that stellar ignition proceeded with surprising efficiency, despite the challenging conditions of high redshift environments. These galaxies appear to be forming stars at rates exceeding 1,000 solar masses per year, sufficient to build entire solar systems every few days. Understanding how such rapid stellar ignition was possible requires new models of gas cooling, fragmentation, and feedback in primordial galactic environments. The study of stellar ignition in dwarf galaxies provides insights into how stellar feedback operates in low-mass systems where gravitational binding is weak. Observations show that dwarf galaxies often experience bursty star formation with periods of intense stellar ignition followed by long quiescent phases. This behavior reflects the strong coupling between stellar feedback and gas dynamics in systems where supernova explosions can heat gas to the escape velocity and temporarily halt star formation. Future observations will probe stellar ignition during galaxy formation through direct detection of population 3 stars or their supernova explosions. The next generation of extremely large telescopes may be capable of detecting individual massive stars and galaxies at redshifts exceeding 10, when the universe was less than 500 million years old. These observations would provide direct constraints on the stellar initial mass function and feedback efficiency during the earliest phases of cosmic star formation. Understanding stellar ignition has revealed deep connections between nuclear physics, gas dynamics, and galactic evolution. The nuclear fusion reactions that power stars operate through quantum tunneling effects that allow protons to overcome electromagnetic repulsion at temperatures far below the classical prediction. These quantum mechanical processes determine stellar lifetimes, energy output rates, and nucleosynthesis products that shape galactic chemical evolution over cosmic time. The efficiency of stellar ignition ultimately determines whether gas clouds become galaxies or remain as invisible dark matter halos. Simulations show that only dark matter halos above certain mass thresholds can maintain the conditions necessary for sustained stellar ignition. Below these thresholds, stellar feedback can heat and expel gas faster than cooling, and accretion can replenish it, preventing galaxy formation despite the presence of substantial dark matter scaffolding. Stellar ignition represents the universe's solution to the challenge of converting gravitational potential energy into visible light through nuclear fusion. This cosmic alchemy transforms the simplest elements into heavier ones while releasing the energy that powers galactic ecosystems and creates the chemical elements necessary for planet formation and life. The moment of stellar ignition marks the transition from invisible cosmic architecture to luminous galactic communities that can sustain the complex chemistry and physics necessary for the emergence of complexity throughout the cosmos. Chapter 6: Feedback Loops. Galaxies regulate their own growth through cosmic feedback systems so sophisticated they make terrestrial ecosystems appear simple by comparison. These galactic feedback loops operate through stellar winds, supernova explosions, radiation pressure, and black hole outflows that can heat, disperse, or compress gas across hundreds of thousands of light years. Understanding these feedback mechanisms reveals how galaxies avoid converting all their gas into stars too quickly while maintaining the delicate balance necessary for sustained star formation. Over billions of years, the concept of galactic feedback emerged from the recognition that galaxy formation efficiency remains surprisingly low throughout cosmic history. Dr. Simon White's analysis of cosmic baryon inventories shows that typical galaxies contain only 10 to 20% of the baryonic matter associated with their dark matter halos. The remaining gas either never fell into the galaxy or was expelled by feedback processes after initial accretion. This low efficiency suggests that feedback mechanisms are fundamental to galaxy formation rather than minor corrections to gravitational collapse. Stellar feedback operates through multiple channels that become important at different stages of galactic evolution. Massive stars produce intense ultraviolet radiation that can ionize surrounding gas clouds and drive photoevaporation flows that remove gas from star-forming regions. These radiative feedback effects can prevent low-mass gas clouds from forming stars while allowing more massive, gravitationally bound clouds to continue collapsing despite the hostile radiation environment. Supernova explosions provide the most dramatic form of stellar feedback by injecting enormous amounts of kinetic energy directly into the interstellar medium. A single supernova explosion releases energy equivalent to the Sun's total energy output over its entire 10 billion-year lifetime, creating shock waves that can heat gas to millions of degrees and drive powerful winds that carry metal-enriched material far from star-forming regions. Dr. Eva Stryker's simulations show that supernova feedback can create galactic fountains where hot gas is expelled to large distances before cooling and falling back toward the galactic disk. The European Space Agency's XMM Newton X-ray telescope has observed these feedback processes in action through detailed observations of hot gas outflows from nearby star-forming galaxies. These observations reveal that stellar feedback creates complex multi-phase gas structures with hot bubbles, cooler filaments, and cold cloudlets coexisting within the same galactic environment. The interaction between these different gas phases determines how efficiently feedback energy couples to the interstellar medium and regulates subsequent star formation. Recent observations from the Hubble Space Telescope have detected massive galactic outflows in distant galaxies that appear to be driven primarily by stellar feedback, rather than supermassive black hole activity. These outflows can transport gas at velocities exceeding 500 kilometers per second across distances of tens of thousands of light-years, effectively removing star-forming material from galactic disks and depositing it in extended halos, where it may never return to participate in star formation. Black hole feedback represents another crucial regulatory mechanism that becomes increasingly important in massive galaxies. As gas accretes onto supermassive black holes, it releases gravitational potential energy that can power jets, winds, and radiation that heats surrounding gas to temperatures exceeding 100 million degrees. This active galactic nucleus feedback can operate with efficiency approaching 10%, meaning that 10% of the rest mass energy of accreting material gets deposited into the surrounding gas, creating heating rates that can exceed supernova feedback by orders of magnitude. The Chandra X-ray Observatory has revealed that black hole feedback operates through multiple mechanisms depending on the accretion rate and black hole spin. During periods of rapid accretion, black holes can produce powerful jets that inflate cavities in the surrounding hot gas, creating mechanical feedback that displaces material and prevents cooling flows. During periods of lower accretion rates, radiative feedback from the accretion disk can heat gas through photoionization and Compton scattering processes. Computer simulations by the Illustristing Collaboration have revealed how different feedback mechanisms interact to create self-regulating galaxy formation. In low-mass galaxies, stellar feedback dominates and creates episodic star formation patterns with periods of intense activity followed by quiescent phases as gas is heated and expelled. In massive galaxies, black hole feedback becomes dominant and can completely suppress star formation by maintaining gas temperatures too high for cooling and collapse. The efficiency of feedback coupling to galactic gas depends critically on the structure and dynamics of the interstellar medium. Recent high-resolution simulations show that turbulent, multiphase gas can absorb feedback energy much more efficiently than smooth, uniform distributions. Turbulence creates density fluctuations that allow some gas to remain cool and dense even when embedded in hot, feedback-heated environments, enabling continued star formation despite strong feedback effects. Magnetic fields play an increasingly recognized role in galactic feedback by influencing how energy and momentum are transported through the interstellar medium. Observations from radio telescopes reveal that many galactic outflows show evidence for magnetic field organization that can guide and collimate feedback-driven flows. These magnetic effects can either enhance feedback efficiency by reducing energy losses to turbulent dissipation or suppress it by providing additional pressure support against outflow acceleration. The timing and spatial distribution of feedback effects create complex regulatory systems that operate on multiple scales simultaneously. Individual star-forming regions experience feedback on timescales of millions of years as massive stars evolve and explode. Galactic-scale feedback operates on timescales of hundreds of millions of years as cumulative stellar feedback heats the overall galactic environment. Intergalactic feedback can operate on billions of years as outflows transport energy and metals to large distances where they influence the cosmic web environment surrounding galaxies. Recent observations of galaxy clusters reveal that feedback effects can propagate across even larger scales through interactions with the hot intercluster medium. When galaxies move through cluster environments, their stellar feedback can interact with the ambient hot gas to create wakes and turbulence that influence star formation in neighboring galaxies. These environmental feedback effects help explain why galaxy properties depend strongly on their cosmic environment. The study of feedback loops in dwarf galaxies has revealed some of the most dramatic regulatory effects because their shallow gravitational potential wells make them highly susceptible to gas loss. Observations show that dwarf galaxies often lose 90% or more of their brownian matter through feedback-driven outflows, creating systems dominated by dark matter with very low stellar masses relative to their total halo mass. These systems provide natural laboratories for studying feedback physics under extreme conditions. Positive feedback represents another important aspect of galactic regulation that can trigger enhanced star formation under certain conditions. Supernova shock waves can compress nearby gas clouds and trigger gravitational collapse that leads to sequential star formation across galactic disks. Similarly, galaxy interactions can drive gas toward galactic centers and trigger massive starbursts that temporarily increase star formation rates by factors of 10 to 100 above normal levels. The role of cosmic ray feedback is beginning to be appreciated as observations reveal that cosmic ray pressures can rival magnetic and thermal pressures in star-forming regions. High-energy particles accelerated by supernova explosions can travel large distances through galactic gas and deposit energy far from their acceleration sites. This distributed energy injection creates an additional pressure component that can drive galactic winds and regulate star formation efficiency. Future observations will probe galactic feedback mechanisms through multi-wavelength studies that trace different phases of gas in and around galaxies. The James Webb Space Telescope can observe infrared emission from warm gas in galactic outflows, while X-ray observatories detect hot gas heated by stellar and black hole feedback. Radio observations trace cool molecular gas that may be either triggered or suppressed by feedback processes operating simultaneously within the same galactic environment. Laboratory plasma physics experiments are beginning to study scaled versions of astrophysical feedback processes under controlled conditions. These experiments reveal how shock waves interact with turbulent media, how magnetic fields influence energy transport, and how radiative cooling affects the propagation of feedback-driven flows. The results provide crucial benchmarks for computational models of galactic feedback that must extrapolate laboratory physics to cosmic scales. The study of feedback loops is revealing that galaxy formation represents a delicate balance between competing processes that operate across vast ranges of scale, energy, and time. Too little feedback allows galaxies to form stars too efficiently and exhaust their gas reservoirs prematurely. Too much feedback prevents galaxy formation entirely by heating and expelling gas before gravitational collapse can proceed. The observed diversity of galaxy properties reflects how different environments and formation histories achieve different solutions to this cosmic balancing act. Understanding galactic feedback loops has profound implications for predicting the future evolution of cosmic structure. As the universe expands and dark energy dominates cosmic dynamics, feedback processes will become increasingly efficient at preventing new galaxy formation while gradually quenching star formation in existing systems. The feedback mechanisms that currently regulate galactic ecosystems will eventually shut down cosmic star formation entirely as the universe evolves toward a cold, empty future dominated by stellar remnants and supermassive black holes. Chapter 7: Cosmic Architecture. The universe builds galaxies according to architectural principles so sophisticated they emerge from the interplay of dark matter scaffolding, gas dynamics, stellar feedback, and cosmic environment to create structures of breathtaking complexity and beauty. This cosmic architecture operates without blueprints or central planning, yet produces galactic forms that follow mathematical relationships, exhibit consistent scaling laws, and show remarkable correlations between seemingly independent properties. Understanding how the universe constructs galaxies reveals design principles that operate across scales from molecular clouds to galaxy clusters. The architectural framework begins with dark matter halos that provide the gravitational foundation for all galactic construction. These invisible structures exhibit universal density profiles that follow power-law relationships first discovered by Dr. Julio Navarro and Dr. Carlos Frank. The Navarro-Frank white profile describes how dark matter density decreases with radius according to mathematical relationships that appear remarkably consistent across the entire range of halo masses from dwarf galaxies to massive clusters. This universality suggests that dark matter architecture emerges from fundamental gravitational physics rather than specific initial conditions. Recent high-resolution simulations reveal that dark matter halos possess complex internal architecture with substructure, streams, and shells that record their accretion and merger history over cosmic time. The Via Lactea simulation shows that Milky Way-sized halos contain hundreds of smaller subhalos that represent the remnants of smaller systems that were gravitationally captured and disrupted. This hierarchical architecture creates preferred locations for satellite galaxy formation and influences how gas flows within the overall galactic system. The transformation of dark matter architecture into visible galactic structure requires gas to cool and condense within the gravitational potential wells created by dark matter halos. But this cooling process follows architectural principles that depend critically on halo mass, cosmic environment, and feedback regulation. Dr. Simon White's analysis reveals that only intermediate mass halos achieve optimal gas cooling efficiency. Small halos cannot retain gas against stellar feedback, while very massive halos heat accreting gas too strongly for efficient cooling to occur. Galactic disk formation represents one of the universe's most impressive architectural achievements, requiring gas to settle into thin, rotationally supported structures that can maintain coherence for billions of years despite ongoing perturbations from stellar feedback, cosmic ray pressure, and magnetic forces. The formation of galactic disks requires precise balance between angular momentum conservation, gas cooling rates, and stellar feedback that prevents the disk from becoming too thick or too thin for stable star formation. Recent observations from the Gaia Space Telescope have revealed the detailed architecture of our own Milky Way disk, showing spiral arm patterns, stellar streams, and asymmetric structures that preserve fossil evidence of past galactic interactions. These observations demonstrate that galactic architecture remains dynamically active even in mature systems, with ongoing processes that continue reshaping structure billions of years after initial formation. The cosmic web provides the environmental context for galactic architecture by determining how gas flows into dark matter halos and how galaxies interact with their cosmic neighborhoods. Galaxies forming along cosmic web filaments receive continuous gas inflow that can sustain star formation for billions of years, while galaxies in cosmic voids must rely on their initial gas reservoirs and typically become gas poor and quiescent. The cosmic web architecture thus determines not just where galaxies form but what kinds of galaxies can form in different environments. Dr. Johann Du Bois's Horizon AGN simulation reveals how cosmic web architecture influences galactic morphology through the angular momentum of accreting gas flows. Gas flowing along single filaments into galactic halos tends to maintain coherent angular momentum that creates disk galaxy architecture. Gas accreting from multiple directions or through major mergers loses angular momentum coherence and creates more spherical elliptical galaxy architecture. The cosmic web's local geometry essentially predetermines the architectural possibilities for galaxy formation. Stellar feedback creates architectural features that regulate galactic structure formation through the creation of bubbles, shells, and supershells in the interstellar medium. These feedback-driven structures can trigger star formation through compression effects while simultaneously creating escape routes for subsequent stellar winds and supernova explosions. The resulting architecture shows remarkable self-similarity across scales from individual stellar nurseries to galaxy-wide superbubble complexes. The role of supermassive black holes in galactic architecture has emerged as one of the most surprising discoveries in modern astrophysics. Correlations between black hole masses and galactic bulge properties suggest that these objects co-evolve through feedback processes that regulate both black hole growth and stellar mass assembly. The architectural impact of supermassive black holes extends far beyond their immediate gravitational influence through jets, winds, and radiation that can modify gas dynamics throughout entire galactic systems. Magnetic field architecture adds another layer of complexity to galactic structure by providing pressure support, organizing gas flows, and influencing stellar feedback propagation. Radio observations reveal that galactic magnetic fields often show large-scale organization with spiral patterns that correlate with stellar spiral arms and gas distribution. Recent simulations suggest that magnetic fields can either enhance or suppress star formation depending on the field geometry and strength relative to gravitational and turbulent forces. The study of galactic architecture in different cosmic environments reveals how external factors influence internal structure formation. Galaxy clusters contain hot intracluster gas that can strip galactic gas reservoirs and truncate. Star formation, creating architectural modifications that transform spiral galaxies into gas-poor ellipticals. These environmental effects operate through multiple mechanisms including ram pressure stripping, tidal interactions, and starvation that cuts off external gas supplies. Recent observations of high-redshift galaxies reveal that cosmic architecture has evolved significantly over cosmic time. Early galaxies appear more compact, irregular, and actively star-forming than their modern counterparts, suggesting that architectural principles operated differently in the dense, rapidly evolving environment of the young universe. The James Webb Space Telescope observations show galaxies at redshift exceeding 10 that appear to violate some scaling relationships observed in local galaxies. The emergence of galactic architecture from fundamental physics represents one of the universe's most remarkable examples of self-organization. Gravity, thermodynamics, electromagnetism, and nuclear physics combine to create structures that exhibit mathematical beauty, functional efficiency, and remarkable diversity despite emerging from relatively simple initial conditions. This architectural emergence suggests that complex structure formation might be an inevitable consequence of cosmic evolution rather than an unlikely accident. Computer simulations of galaxy formation are beginning to reproduce observed architectural features with increasing fidelity as they incorporate more complete physics and achieve higher resolution. The FIRE simulation project can now model individual stellar nurseries within galaxy formation simulations, revealing how small-scale physics influences large-scale architecture through stellar feedback, turbulence, and magnetic field amplification. These simulations show that realistic galactic architecture requires physics operating across more than 10 orders of magnitude in scale. The study of dwarf galaxy architecture provides insights into how cosmic construction operates under extreme conditions where stellar feedback can dominate gravitational forces. Dwarf galaxies often show irregular architecture with asymmetric structure, active star formation, and evidence for gas outflows that create extended halos of hot, metal-enriched material. These systems demonstrate that galactic architecture can maintain coherence even when feedback effects are strong enough to substantially modify the underlying dark matter distribution. Future observations will probe galactic architecture during formation through gravitational lensing studies that can resolve structure in distant galaxies with unprecedented detail. The next generation of extremely large telescopes will be capable of studying stellar populations, gas dynamics, and magnetic field structure in galaxies observed when the universe was less than 1 billion years old, revealing how cosmic architecture principles operated during the earliest epochs of galaxy formation. The mathematical relationships that govern galactic architecture suggest deep connections between cosmic structure formation and fundamental physics, scaling laws that relate galaxy mass to size, rotation velocity, and surface brightness may reflect underlying physics principles that operate universally. Throughout cosmic structure formation, these architectural relationships provide constraints on dark matter properties, feedback physics, and the nature of cosmic web assembly. Laboratory studies of self-organizing systems are beginning to reveal general principles that might apply to cosmic architecture. Experiments with granular materials, plasma physics, and fluid dynamics show how complex structures can emerge from simple rules and random initial conditions through mechanisms analogous to those operating in cosmic structure formation. These studies suggest that galactic architecture might represent specific examples of universal self-organization principles that operate throughout nature. Understanding cosmic architecture reveals that galaxy formation represents a remarkable example of emergent complexity where simple physical laws combine to create structures of extraordinary beauty and functionality. The architectural principles that govern galactic construction operate through gravitational dynamics, thermodynamic processes, electromagnetic interactions, and nuclear physics that organize matter and energy into forms that can sustain complexity for billions of years. This cosmic architecture provides the foundation for stellar ecosystems that create the chemical elements and energy sources necessary for planet formation and the eventual emergence of life throughout the universe. Chapter 8. Galactic ecosystems. Galaxies function as vast cosmic ecosystems where stars, gas, dust, magnetic fields, and dark matter interact through complex cycles that regulate energy flow, chemical enrichment, and structural evolution over billions of years. These galactic ecosystems exhibit properties remarkably similar to terrestrial ecosystems: energy networks, material cycles, population dynamics, and feedback relationships that maintain overall system stability while enabling continuous evolution and adaptation to changing cosmic environments. The stellar ecosystem represents the most visible component of galactic ecology, with star formation and stellar evolution creating energy and chemical cycles that sustain galactic activity over cosmic time. Massive stars provide energy input through radiation and stellar winds, while their eventual deaths as supernovae inject kinetic energy and heavy elements that regulate subsequent star formation. This stellar energy cycle operates like a cosmic metabolism, converting gravitational potential energy into light, heat, and chemical complexity. Dr. Robert Kennicott's studies of star formation laws reveal how galactic ecosystems self-regulate through feedback relationships between gas density, star formation rate, and stellar feedback intensity. The Kennicott-Schmidt law shows that star formation rates correlate with gas surface density according to power-law relationships that appear universal across different galaxy types and cosmic environments. This correlation suggests that galactic ecosystems maintain quasi-equilibrium states through self-regulating mechanisms that prevent runaway star formation or complete quenching. Gas cycling represents the fundamental metabolism of galactic ecosystems, with continuous flows of material between different phases: molecular clouds, ionized gas, hot bubbles, and circumgalactic medium. The Atacama Large Millimeter Array ALMA has traced these gas flows in unprecedented detail, revealing molecular gas streams that feed star formation, ionized gas outflows driven by stellar feedback, and circumgalactic gas reservoirs that provide future fuel for continued galactic activity. Recent observations reveal that galactic ecosystems extend far beyond visible galactic boundaries through extended gas halos that can contain more mass than the galaxy itself. The Cosmic Origins Spectrograph on the Hubble Space Telescope has detected these circumgalactic gas reservoirs through absorption line spectroscopy, showing that they contain multiple temperature phases and exhibit complex kinematics that reflect ongoing interactions with stellar feedback, cosmic ray pressure, and environmental influences. The chemical ecosystem within galaxies operates through stellar nucleosynthesis cycles that gradually enrich the interstellar medium with heavy elements essential for planet formation and potentially life. Different stellar mass ranges produce different elements. Massive stars create oxygen, silicon, and iron through explosive nucleosynthesis, while intermediate mass stars contribute carbon and nitrogen through asymptotic giant branch evolution. This chemical diversity creates galactic ecosystems with spatially varying metallicity patterns that reflect star formation history and gas mixing efficiency. Magnetic field ecosystems provide additional organization to galactic structure through field amplification, transport, and dissipation processes that influence gas dynamics, cosmic ray propagation, and stellar feedback efficiency. Radio observations reveal that galactic magnetic fields exhibit complex topology with spiral patterns, reversals, and turbulent components that reflect the interplay between differential rotation, turbulent motions, and cosmic ray interactions. These magnetic ecosystems can either enhance or suppress star formation depending on field strength and geometry. The dark matter ecosystem provides the gravitational framework that enables all other galactic ecosystem components to function effectively. Dark matter substructure influences satellite galaxy orbits, creates preferred locations for gas accretion, and determines the overall gravitational environment that regulates galactic structure evolution. Recent simulations show that dark matter ecosystems remain dynamically active throughout cosmic time through ongoing accretion, subhollow disruption, and tidal heating effects. Dr. Romil Dave's simulations of galactic ecosystem evolution reveal how different components interact to create emergent properties that aren't predictable from individual process studies alone. These simulations show that realistic galaxy formation requires ecosystem-level modeling that captures interactions between star formation, stellar feedback, gas dynamics, magnetic fields, and cosmic ray transport. Simple prescriptions that treat these processes independently fail to reproduce observed galactic diversity and evolution patterns. Environmental influences on galactic ecosystems operate through multiple mechanisms that modify internal ecosystem functioning. Galaxy clusters contain hot intracluster gas that can strip galactic gas reservoirs through RAM pressure effects, fundamentally altering ecosystem energy balance and chemical cycling. Tidal interactions during galaxy encounters can trigger enhanced star formation, redistribute angular momentum, and modify magnetic field structure across entire galactic systems. The ecosystem approach to understanding galaxies has revealed unexpected connections between apparently unrelated galactic properties. The correlation between supermassive black hole masses and galactic bulge properties suggests that central black holes participate in ecosystem regulation through feedback effects that influence star formation efficiency across entire galaxies. Similarly, correlations between galactic rotation curves and surface brightness profiles indicate that dark matter, stellar populations, and gas dynamics maintain coupled ecosystem relationships. Recent studies of cosmic ray ecosystems within galaxies reveal how high-energy particles participate in galactic regulation through pressure support, heating effects, and influence on magnetic field structure. Cosmic rays accelerated by supernova explosions can travel large distances through galactic gas and deposit energy far from star-forming regions, creating distributed feedback effects that modify gas cooling and star formation efficiency throughout galactic ecosystems. The European Space Agency's Gaia mission has revealed ecosystem-level organization in stellar populations within the Milky Way, showing how stellar streams, moving groups, and chemical gradients preserve fossil evidence of ecosystem evolution over billions of years. These observations demonstrate that galactic ecosystems maintain complex internal structure even as they evolve continuously through stellar birth, death, and gas recycling processes. Galactic ecosystem stability requires careful balance between energy input from star formation and energy loss through radiation, outflows, and cosmic ray escape. Computer models show that ecosystems can exhibit different stable configurations, actively star-forming systems with high gas fractions and continuous cycling, or quiescent systems with low gas content and minimal ongoing activity. Transitions between these ecosystem states can be triggered by environmental changes, major mergers, or internal instabilities. The study of ecosystem disruption during galaxy mergers provides insights into how galactic ecosystems respond to major perturbations. When galaxies collide, their ecosystem components of stellar populations, gas reservoirs, magnetic fields, and dark matter halos interact through complex processes that can either trigger enhanced activity or completely restructure ecosystem functioning. The antennae galaxies provide a nearby example of ecosystem disruption and rebuilding during an ongoing major merger event. Dwarf galaxy ecosystems operate under different physical conditions than massive galaxies due to their shallow gravitational potential wells and high surface-to-volume ratios that make them more susceptible to external influences. Stellar feedback can more easily disrupt dwarf galaxy ecosystems, creating bursty star formation patterns and extensive gas outflows that modify ecosystem composition. These systems provide natural laboratories for studying ecosystem functioning under extreme conditions. Future observations will probe galactic ecosystem functioning through multi-wavelength studies that trace different ecosystem components simultaneously. The James Webb Space Telescope can observe stellar populations, gas dynamics, and dust distribution, while X-ray observatories detect hot gas phases and cosmic ray interactions. Radio observations trace magnetic fields and molecular gas that provide the raw material for continued ecosystem functioning. The ecosystem perspective on galaxy formation has revealed that successful galaxy formation requires not just assembly of mass and energy, but development of self-regulating systems that can maintain function over cosmic time. Ecosystems that develop effective feedback regulation can sustain star formation for billions of years, while those that fail to achieve ecosystem balance either consume their resources too rapidly or become quenched by excessive feedback effects. Laboratory ecosystem studies are beginning to reveal general principles of self-organization and regulation that might apply to galactic systems. Experiments with bacterial colonies, social insect communities, and artificial life systems show how complex regulatory behaviors can emerge from simple interaction rules operating at individual agent levels. These studies suggest that galactic ecosystem regulation might represent specific examples of universal self-organization principles. Understanding galactic ecosystems has profound implications for astrobiology and the search for potentially habitable worlds. Ecosystem functioning determines the rate of heavy element production, the efficiency of planetary system formation, and the stability of stellar radiation environments that influence planetary habitability. Galaxies with well-developed, stable ecosystems provide the most favorable environments for the emergence and persistence of complexity throughout cosmic history. The ecosystem approach to galaxy formation reveals that galaxies represent some of the most complex self-organizing systems in the universe, exhibiting emergent properties that arise from interactions between multiple physical processes, operating across vast ranges of scale, energy, and time. These cosmic ecosystems create and maintain the conditions necessary for stellar formation, chemical evolution, and potentially biological development through regulatory mechanisms that operate without central control or external design, demonstrating how complexity can emerge naturally from simple physical laws operating in suitable cosmic environments.